Hello, everybody. Hello, world out there. So this is Friday. So welcome back to iConnect Talks again. This is a great platform for connecting everybody. So my name is Misu Kim. I'm an assistant professor from Sungkyunkwan University, South Korea. And I serve as a moderator for today's iConnect Talks. And today with me, Professor Martin Tuo from Iowa State University will be as a moderator here for us. And today, so this month, so this May, I'm very pleased, and then I take the privilege to introduce all of these amazing stars scholars out there. So last week we had Professor Buise Lee, and today we have two amazing rising stars, who's a Professor Howard Lee and Professor Fan Wang. And next week we're going to have Professor Manish Chawla, and the following week we're going to have Professor Harry Atwater. So, so today we have two amazing, as I said, today we are going to have two amazing rising stars who've been awarded the Rising Stars in iConnect in the beginning of this year. So the first speaker will be Professor Fan Wang from the University of Technology, Sydney. And this is my great pleasure to introduce him here. And Professor Fan Wang, the stage is yours here.
Yeah, hello everyone. Yeah, I'm gonna share my screen. Okay, yeah, thanks for the introduction. It's my great honor to be here to present my work. So today I'm gonna talk in something about rare earth doped nanoparticles for biophotonics application. So it really began, I want to introduce a little bit of my group. So recently I just transferred my group from UTS to Beihang University, and we are working on biophotonics, and soon we're gonna also working on the quantum optics and also nanomaterials. And today, but I still gonna focus on to the biophotonics, which gonna be the superrise, tweezer, and single particle tracking. And I also want to mention that in my group, we're also gonna doing the on-chip superrise and laser cooling, and also superrise solution characterization. So we are looking for postdoc and HDR students. So now let's begin my talk. First of all, I'm gonna introduce what is this biophotonics, because people usually heard this photonics. So biophotonics is basically just using the photonics technology to do the biological research. So you may think that we already have tweezer and knife doing the normal biological experiment. How come we still need this photonics technology? The reason is recently the things we want to study come to smaller and smaller, actually from some biotissue and shrink the size down to a single cell, and even smaller, much smaller than single cell, like each of this organelle, and also some biomolecules. So those, since the size is really, really tiny, it's much smaller than your tweezer and a knife. So you have to use the smallest things to study of them. The reason why we want to study them, because if you think the cell is full with the gear, and if you want to know what's the working function of the live or the single cell, you have to study, you have to see the individual gear, and you have to put something to inside to study what's the interaction between them. So my research focuses on to three parts, like how to see them, super resolution, and how to manipulate them, or give some interaction. So this is optical tweezer. And another one is the sensing of the surrounding. So this is the optical sensing. So I'm gonna introduce them one by one. First is the super resolution microscopy. So supervised imaging, or the optical, is part of the optical imaging. And optical imaging already been have really, really long history. But there's some limitation, which is if the feature really, really small, like smaller than 200 nanometer, usually we couldn't see them clearly, like the things I block here. The reason is because of diffraction limitation. And in 2014, this three smart guy developed the super resolution microscopy. And then for the first time, we can show those beautiful things, the smaller feature like nanoparticle, virus, and even DNA. And with those technology, we have much better understanding what's the fundamental of the life. And currently, they already have many different type of super resolution technology. And I'm gonna introduce the three, the three basic one. One is the STAD, stimulated emission depletion, storm, and structured illumination microscopy. So these are three major, three main technology. So for the STAD, it's basically using the one, it's got the Gaussian excitation as normal beam and got diffraction limitation. So the beam size, you couldn't control it. They have the smallest size. And for the depletion, you have a donut beam. So if something, some particle or some so this donut beam, just like an eraser, can basically cancel the emission inside or modulate the lifetime by using the gating system. You can select your emission. So therefore, if you add in these two together, you have a really small point square function. So this is the working function of the STAT. So this one generally give you really high resolution, but the drawback is if you want to have really high resolution, you have to shrink the size of the middle hole. And for doing that, you have to increase your laser power. So therefore, usually for STAT, basically don't have really good biocompatibility because you need to use high laser power. And storm is another technology. So for this one, it's based on the statistic. If you make your molecule, each of the molecule blink, give some a random blinking, and when they blink once and you just record the central position, and then if you do the statistic one by one, and finally you have a really high resolution come out. So therefore, for this one, because it's based on the localization, so the resolution is really high, even higher than the STAT. And also have really good biocompatibility. The reason is you just use a really small power, but the problem is you have to waiting for each of them blink once. So therefore, your image time is really long. And another thing is each of these die can only blink once or twice. So it doesn't work for really long term. And the structured illumination microscopy is a really good one. So the working principle is just by you changing the structure of the light. So for example, I give a really simple demonstration. If you have some feature here, and if you have some finger, you basically can pick up the beating frequency between your illumination and your sample. And once you can pick up those kind of resolution, and you can modulate your result. And so therefore, for this method, it can be really fast because it's wide field, it's a wide field super resolution, and also illumination intensity is not that high. Only a little bit of challenge is the resolution not that high. I'm gonna mention about this later, but you can use the nonlinear SIM to upgrade your SIM and make higher resolution. So these are different technology, and there are also many really new technology and solve some problem, but the majority challenge for this field is if you look at them, they all have limited working depth. And the reason of this is basically just from the absorption. And this has been a challenge for all the super resolution technology. So the reason is if you think, it's basically from the absorption. So if you just use your hand to block some of the beam, you will see it's come to red. The reason is basically the red color of the light will be absorbed by your hand, so by the biotissue. And currently, most of this super resolution technology is building basis on the visible beam. So therefore, for this visible beam, the absorption is really high. And to solve this one, actually, it's quite easy. You just need to shift your working wavelengths to biological window, which is the near infrared range. And by doing that, you basically can have the super rise. But the challenge is how can we do that? Because we know that currently this only few type of the near infrared dye is working really well. So for doing that, what I did is using optical conversion nanoparticle to solve this problem. So this kind of nanoparticles is made by nanocrystal and embedded with the sensitizer and also the activator. So the sensitizer will absorb the near infrared light and do the energy transfer to the activator or the emitter to give you the emission, and actually can have like a full color emission. And if you look at the energy level, it's quite interesting because the absorption for the sensitizer, like ytterbium, basically absorption is linear. So therefore, the absorption cross-section is like higher than no-linear absorption. And if you look at the emitter, this is a no-linear energy transfer. So for this energy transfer, because we have several real energy level here, so when the carrier catch up to go to the higher level, it's more like just a catch on some ladder. So just going one by one, jump to the top, so got a really high chance, high efficient to do the conversion. So compare with second harmonic generation or 2-photon absorption. So this material have much higher like conversion rate. And if you look at the rate equation on different energy level, it's really, really interesting because we have so much parameter we can play with them. And so if you plot so on this figure, you can see that it is the power dependent with different doping concentration, basically have different profile, but you can see it's just no linear. And this no linear come from many parameter. First one is this K, so this is a cross relaxation, means like in some level, when you one carrier jump from the top with the medium, and they're gonna give this energy to another one from bottom or the fundamental level to the intermediate level. And also it's got the, like if you look at the rate equation, you got this transfer rate. And for some level in higher level, also dependent on the carrier in other level, because you see they're multi-n multiply together. So this gives you a really beautiful superlinear curve. Also it have the saturation. So saturation means like we can only dope certain amount of sensitizer and emitter inside the system. And if you look at the different rate equation, which is in different energy levels, they all have different response. So therefore, we actually can use those parameters to design the different method to doing the superrise. So next, I'm gonna introduce how can I do that one. And before that, I want to mention what's the benefit of this nanoprobe compared with the other one. Firstly, because this is atomic emission, so it doesn't quench and it doesn't blink, not like your dye. So you can do it for like even for 1 day or several days for the fluorescence experiment. And another thing is like because you can use near infrared beam to excite your particle, and the emission also like quite far away from excitation. So basically you can do the really large anti-stock emission, and you pretty much have background free imaging. So you can see it's really clearly just we can only see the emission, not any autofluorescence emission. And depends on different doping element. You can also change the emission color. And it's really uniform because for each of this particle, you got thousands of emitter. And so therefore, the emission is really uniform, usually only like 10% intensity different for different one for one batch of particle. If you remember the previously I mentioned the rate equation, basically the lifetime can be controlled just because all the parameters can be tuned by changing the average distance between the different ions. So therefore, you can change the lifetime to do the lifetime multiplexing. And also, it's really, really bright. It's comparable with quantum dot. So if you put those particles inside a thin layer like this one, transparent layer, you basically just use laser scanning, you can see the emission. So this is a real-time radio. So you basically can do the real-time displaying in 2D or even 3D. And the most amazing thing is basically this, for me, is this nonlinear response. So I'm gonna use this nonlinear response to design the supervised imaging method. And so therefore, for this nanoparticle, it's just like a really good weapon for me. And when all the technology dress up with this like upconscious nanoparticle, you pretty much can enhance this penetration depth. Just because for this particle, you can use nonlinear, you can use like near infrared excitation and also near infrared emission. So now the challenge come to like how can we just use this nanoparticle to design the supervised method? So the first work to like using this particle for the super resolution is based on the cross relaxation by Professor Dai Jin's group. So what they did over here is like they heavily doped these thallium ions. And once they have like many ions inside this system, and because of cross relaxation, when one carrier jump from this like 1D2 level to the intermediate level, at the same time, it will excite another one from the ground level to the medium level as well, because these two energy are matched together. So eventually, you're gonna build some population inversion in this intermediate level. And once you do that one, if you have another laser match with this energy level, you're gonna trigger all the carriers down. And then just like in the letter, you just remove some of the letters, so you never can get the carrier come to the pop again. So experimentally, what you're saying is like if you're shining one laser, 980 laser, you can see the bright emission from the particle. But if you're shining another laser at the same time, it pretty much switch this emission off. And this is because of photo avalanche effect. And using this one, we can build some stat experiment. So using the 980, we can make this light up, and the 808, you can just make the depletion. And here you can use a continue because you really just switch the emission off. And using that one, and they basically achieved a 30 nanometer. And later on, they found that using this one, actually you do not need using this like stat. So this is predicted by the by Alter. So what he did is like he studies that if you have photo avalanche, basically your power dependence gonna be like really nonlinear, and depends on the n, which is the number, like how many photons equivalent to one photon come out. And if this n is really big, and if you're just doing the scanning by selecting your excitation in certain range, you directly can have this superrise. And in 2019, so there's another group already achieved this one, but the resolution not that high, only 210. But what you need is just a normal confocal microscope. And later on, we also found that this one can be much enhanced by just reduce the power. So by just reducing the excitation power, we can control the carrier in different level. And what we achieve is like by reduce the power onto just 1 milliwatt, basically your resolution can go down to like 130 or something for directly scanning, and for stat also can go in really down, and even go to like 20 nanometer. So by doing that, we pretty much solve this biocompatibility problem, because we just need a really tiny bit power to do the stat. But since like the above method and also these two methods include our method is based on the emission from upper level, so still on the visible light. So the challenge is like what we really need to do is just switch this emission totally back to the near infrared. So this is why we designed the one method of this one. So switch this visible light to near infrared. So this is building on this saturation. So what we did, just using a donut here. So I put a donut here, not because I'm hungry, close to dinner time. It's just because like we just only need using one donut beam, we can achieve this superrise. So we pretty much build it based on this power dependent. If you look at this one, it's really nonlinear, and then have beautiful saturation here. Means like if you further increase power beyond 1 milliwatt, basically you couldn't see much of the intensity change. They couldn't increasing. Therefore, if you use a one donut beam and do the scanning, you have a donut principal function come out as well. But when you increase your laser power, because it's saturation, your hole in the middle gonna be shrinked really tiny and beyond the diffraction limitation. So this is how can you do the superrise. And experimentally, we can send this donut beam, do the scanning, and all the way down through this 100 micrometer tissue, you will see that the blue light is basically already fade off, but the 800 nanometer light still have something. And amazingly, if you look at this pattern, is there a small hole in the middle? So this is a 50 nanometer. Actually, by changing the power, increase a little bit of power, you can maintain this 50 nanometer all through this 100 micrometer tissue. And you can see that if we put some particle inside this like tissue layer and in confocal, you couldn't solve this one. And by using our method, you can see some black hole here. And by just using the deconvolution, you can have the positive image come out here. So this is how can we solve this absorption. And further on this one, we also think how can I go even deeper. But if you want to go even deeper, you get subject to this scattering problem. And to solve this one, the reason why we want to solve this one, because we want to do the imaging for this organoid. So organoid is kind of like mimic the organ. So it's more like you take some stem cell from your heart, from your liver, and you make some like mimic organ, and they got same working function. So this is amazing. You can try different medicine, different things on this one because it shares the same kind of tissue with human body. But the only challenge is like for this organoid, the cell density is really, really high. So from this image, you can directly see that. So everything is not transparent. So the cell density is basically 4 times higher than the normal tissue. So what we did is just design some basal LG beam to solve this one. So basal beam is kind of so-called is like a non-diffractive beam. So it's building based on the interference. So you got the hexagon or conic lens, and all the beam in from all direction and have interference. So they have really, really long depth of field or have really long focus. So over this time, if you block some part of the beam, it doesn't really matter because the rest of the beam still got an interference. So therefore, if you use this basal beam and added this basal beam to our like our donut beam, we have the basal LG beam or basal donut beam. So in this simulation, if you put some scatter in some position, basically you maintain the good focus, still like a really good donut shape. So this showing that like we can use this donut basal donut beam to do the superrise, and we did that. So we can just tracing out each of the single nanoparticles inside this organoid, and so we can see like with the time with the different time for different type of the what's the nanomedicine distribution inside this organoid. So but there's some challenge. So previously I only mentioned that we can use donut to do the imaging, but with donut have some limitation, which is if you look at the spatial domain or the spatial frequency domain, you will see the pink is the donut beam, and the OTF. So this OTF means like all the frequency signal inside your figure. If you use donut beam, there's some missing frequency over here. It means that you can think if your donut, there are some particle arranged in some space, it's actually match with the pattern with the donut, so it's never fade off. So these things happen here. So for this spacing, basically for our resolution, it should be really clear, but you see that it couldn't solve this dot pattern. It's just because you have missing the frequency, not because your resolution is not good enough. So the highest resolution is really high, but there's some missing frequency. But the Gaussian beam is actually good with this lower frequency. So previously, the researcher has been done is like adding these two together in the Fourier fusion, and then they can solve this problem. And for us, we have some even better way to doing that one. So this is an example that if you have some like mooncake or a flower pattern, you see this is not resolved really good because they have this frequency missing. So what we did here is if we put a donut beam into our system, because we have for all nanoparticle for different energy level, we can have different response. So therefore, for the 800 nanometer, and we basically have like a Gaussian emission because they all already saturated. And for the 740 is also near infrared emission, you have the donut. So therefore, if you look at the free domain, basically the 740 is good at like the larger frequency range, and for the 800 one is good at the lower frequency one. So what we did is just in the free domain, free transfer, put this information together and do the free transfer again, and then you have much better image here. And if you look at here, just compare with another method like subtraction or directly deconvolution, this fusion gives you much better control on the aberration. And at the same time, you maintain the good resolution of 50 from this donut beam. And using this one, we can even resolve some like fancy feature, like just some letters supervised, and also a panda here. So I have to mention that you see this panda is got a little bit blurred. The reason why is we couldn't control well to put the nanoparticle in this hole. So what we did here is just using the fib to punch lots of hole in the substrate and put a nanoparticle inside to do the imaging, but we couldn't control make one hole, got one particle. So what you're seeing here, just a filling by metal. So it's showing like really regular pattern here, but if you film is or nanoparticle, it's quite hard. But even though you compare with the confocal, you can see that we have really good resolution and control on the good control on the aberration. And if you look back at this like mooncake structure again, and then you find out it's actually basically lots of dot here, and rather than this blurring feature. So so the first method we have been talking about is basically based on the single beam scanning. So it does solve this penetration depth problem, but it's raising up another problem. It's like a little bit slow. If you want to scan for a really small area, it's fun. But if you want to scan something like organoid, it's really, really big. It's like hundreds of micrometer. You need to take a few hours to do the scanning. So this is why how to increase this image speed is another challenge. And over here, I want to introduce this structured illumination microscopy. So for this method, as mentioned before, it's based on the beating frequency with the illumination pattern with your sample. And you can also sync this from the more pattern one or more finger. So if your sample have some uncertain frequency, let's say the frequency is changing from like really low to really high, and your illumination is going to be in some other type of frequency. And if you overlap this pattern, you will see the more finger. And you will see that in the frequency beating up, basically your larger finger going to be changed. So therefore, if you rotate like 180 degree and by doing lots of pattern, you basically finally can find out what's your pattern, what's your sample pattern. So this basically is the working mechanism. And if you think from the free domain, it's actually it's easier way to think. So basically, the reason why we couldn't see this really small feature is just because of our back aperture of the object lens. So this is object lens. The back aperture is just like a low pass filter. For some other information beyond this aperture couldn't be transferred to come out. And if you put your illumination as some pattern, it's more like you pushing your central at the K space. And if you have the resolving this pattern again, basically you can have like the information beyond this one because you push the center of the K. And by solving you need a 3-phase and also 3 direction to solve this different pattern, and then putting them together to the Fourier transfer again, you can have much better resolution. Actually, not much better, only twice, because if you look at this one in K space, you only increase it twice. So that's the limitation of normal SIM, but you can also build this saturated SIM. What I mean is like if you shine on the pattern, but if you increase the power, your response is going to be changed. And then you can have some like higher information. And then by doing this one, you can like further increase your power and doing many direction. And then you can solve this, then you have much better resolution. But the challenge is similar with the STAT. So if you want to give some saturation, you have to use really, really high power. And remember that on this situation, is using the wide field excitation. So you need extremely high power to doing that one. But if you use an all nanoparticle, because we have this amazing superlinear one, basically we can take an advantage from this superlinear to design some low power, no linear sim. So that is the example. If we use in different doping concentration, you will see that our power dependence can be different. And if you doping with 8% thulium, you will see that it's really, really nonlinear, means that if you use some finger, only high intensity part will have the emission. So if you plot with the in the frequency domain, you will see that as we heavily dope with thulium, your harmonic peak will become up. And this showing that this material is really good to doing the nonlinear thing. And experimentally, we did that. So we put a nanoparticle one inside of this one, and we can do the nonlinear thing. So currently limited by this like working wavelength. So we only got like 130 nanometer for the resolution, but we try to further enhance this one. And the emission, basically we got almost a video rate, so it's like 1 Hertz. So we can see some dynamic using this like superrise. So it's published in Cover of the Nanolighter. And later on, we also found that we actually can also, based on this particle, doing some like multiplexing, because we can tune in the lifetime. So if we shift the lifetime, and we can do the lifetime supervised, and also we also have different colors, so have a 2-dimensional matrix. So next, I want to talking about this one. So this is not from my work, but I'm quite excited about this one, because recently, last year, like so 3 big guy author, not 3, like all the authors, pretty much big guys, they published a paper together showing that in this system, if you're just using 1068 to pumping of the thulium itself, have some like photo avalanche. So this gave the power dependence up to like 22. So it's really, really high. And later, and for this one means that if you just directly do the scanning, you can have resolution up to like 60 nanometer. So this is a really high resolution, and you do not need to do any modification. And for this year, Professor Qiu Qiangzhang also mentioned that if you not using this one, but using another like ions and with also this ytterbium, you can transfer this like photo avalanche to any of the emission, and they achieved actually 46. What I mean is like, so this technology is really, really interesting. If you add in all of this like material and then using to the supervisor, we can achieve even better and even simple system for much better resolution. So this is pretty much the things I want to talk about the superrise. And next, I'm gonna talk a little bit about the optical tweezers. So optical tweezer is a technology using laser beam to manipulate small particles like this one. You can play some video game. You can also do the 3D, you trap 2 and roll it up. And if you want, you can also trap a small nanoparticle, so from micro to nano. So this is dark field 50 nanometer golden nanoparticle. So if the particle is really big, you can think basically your beam just refracted by your large particle sphere, and any redirection of the laser beam basically have the momentum change, and this momentum change gonna give you the force. And if you calculate this one, it's always drive you to the high intensity part. And if the particle is really, really small, it fell into the really range. So this is the over nanoparticle. For that one, you can think the particle just loss of dipole, and the dipole will have a Lorentz force. And if your light field is strong enough, you can calculate and zoom this up, divided into the scattering. The scattering force basically is the radiation pressure push the particle away, and also the gradient force will form from potential well, and the particle will go into the bottom of the potential well. And So over this one, the reason why I want to show this formula because I want to see that this is highly in relation to the refract index of the particle. So this is a 3D modulation. You will see that the particle can be confined in the 3D potential well. So tweezers already have many applications like basically doing the force measurement for the strain force of the DNA, and also can manipulate some organ like the air stone inside the zebrafish, and also can trap some like a red blood cell inside the living mouse. And also you can trap the particle inside the cell and doing some sensing. And amazingly, you can also trap the two atom and put it but this is doing in the vacuum. So you trap the two atom and merge them into a molecule. And so this one is interesting recently because we have lots of like nanosensors. So you can trap the nanosensor and trap golden nanoparticle heating and doing the heating and doing the tweezer and doing this temperature sensing at the same time. And of course, you also trap in the air doing some like 3D display. So because it's really useful, so this optical tweezer has been obtained the 2018 Nobel Prize. But the tweezer for the last 20 years always have one challenge, which is like have to have this refractive index mismatch. So as mentioned before, the tweezer is based on the interaction. So if you don't have the refractive index mismatch, just like this, like a jellyfish inside this water, if the refractive index is really matched with the surrounding, basically your light will pass through this one. So don't have much interaction. So this gives some challenge. Like when you have this like weak interaction, your scattering gonna be small and your force gonna be small. So the same like maybe doing some trapping some like a biological particle or even optical conversion, because all of the nanoparticles have been shown like trapped by optical tweezer. But if the particle is really large, you have like really strong force. When the particle is smaller, you don't have strong force. And if the permittivity or refractive index is really small and you don't have much force. So our optical conversion is actually bottom here. So really small refractive index, also really small, only 1.4. So also got a limited scattering. So because the force is really small, so there already have some other researchers study how to enhance this like force. So one of them is from Professor Daniel. So just use a surface charge and you can increase this one. But in our experiment, we found that it's only got a tiny bit increasing on this one. Another force is the near resonance radiation force, a little bit like laser cooling force, but eventually this one from calculation only increased like 1% or 2% of force. And experimentally, another people use a super radiation, and by using this one, basically all the defect in NV center work like one big dipole, and it does have enhancement, but only enhance 20%. So the enhancement is really limited. So what we want to do here, so it's really limited. So this is one problem. So enhancement is really limited. We want to enhance the force. And another limitation comes from this detection. As I mentioned, this M is the ratio between the refractive index of the particle and the surrounding material. So if this match together, means like your scattering is really, really low. You even couldn't detect your force. So for us, firstly, we designed one method based on the machine learning and the video tracking. We can do the three-dimensional map of this like nanoparticles position during the trap. And then we can calculate what's the force on the three-dimensional. Actually, we achieved a few hundred atto-Newton force. So by doing that, we found that actually in our nanoparticle, because we dope lots of iron, so we have a really strong iron resonance enhancement. So this enhancement is really amazing. And so for this one, it basically makes the ytterbium ion have the resonance, so have the 3 level. If you look at this 3 level, each of them gonna give you the enhancement that we can substantially increase this suspectivity. And eventually you can add these three, enhance the suspectivity together. And finally, you can enhance this trap stiffness. So this red circle is our laser beam. And you can see that for the really like a low refractive index nanoparticle, like 1.5 nano, refractive index 1.5, so you couldn't trap them because your position sometimes gonna jump off from the trap. But for our nanoparticle, benefit from this ion resonance effect, the trap stiffness is really high. So the point distribution is really density. And using this one, we found that actually for all kind of this kind of lanthanide ions, we have the this ion resonance effect, and you see that the response have some like resonant shape. And using this one experimentally, we do the scanning for different wavelengths. We see the trap stiffness have some variation, and it's got much enhancement on the trap stiffness because those values really high. So we compare this with the normal golden nanoparticle, like in same size, basically the trap stiffness is like got 30 times enhancement, but keeping in mind that the refractive index of these nanoparticles is much smaller than the golden nanoparticle. And we also found that apart from this resonant enhancement, the zeta potential also gave some enhancement. And we do study of this one, but we found that the enhancement is just really tiny. So the majority one for larger particles from this resonant effect. And based on this one, we can trap one nanoparticle, low refractive index, really stable. And if you tune in the surrounding material, like make some sugar, water, refractive index totally match with this upmotion nanoparticle, you still can trap. So this is the first time doing that one. And the amazing thing is like we can also dope this nanoparticle on the surface of single cell. Once we do that, we pretty much, so this one is like we put it all the nanoparticle on the surface of the cell. And doing that one, we can enhance the force interaction. So we call this like the force dye. And doing that one, you see that for the normal cell, and we use two different color of laser, the ratio is same. But if we're doing this one, this red beam, this red circle is like we use another, we doped with nanoparticle, and you will see the little bit random. But if you reach like arrange them according to their emission, you will see the force is increased. So it means that we can use this one to enhance or force on the biosample. It means that if you dope this nanoparticle inside the cell, you can even like just control each individual of the organelle. So, and upon of this one, apart from just increase this like force, we can also tune in the refractive index for tuning the scattering feature, because the time I'm gonna generally show this one. So using the iSCAT, you can tracing up with this value, you will see that for this different type of nanoparticle, we can change the really scattering spectrum. And so for different wavelengths, basically your scattering intensity gonna be totally different. For really scattering, your normal one is gonna be just keep decreasing, but for this one, you can tune in them. And with this one, because you've got emission, you can also build up some multiplexing the eye scattering microscopy, like you can track in all this dot inside some tissue or inside the living cell. So this is pretty much everything about the nanoscale optical manipulation. And the next, because of time issue, I'm gonna just quickly flash off the single particle tracking. So what we did is firstly getting some method to tracking each of the nanoparticle. We can real time tell which one is single, and we can achieve the viscosity sensing. Upon this one, we also build another one to like single. It's built on the self-interference. So basically we can do the nanoscale sensing on this one for different position. We can just in 50 Hertz and with resolution smaller than 1 nanometer. So yeah, this is pretty much everything I want to mention today. Because limited time, I didn't mention the single particle tracking. Hope you enjoyed the talk. So I also want to acknowledge my group member. So I also want to acknowledge my collaborator, especially Professor Da Yongjin, Peter Reis, and Professor Jagadish, and also thanks for my founding agent, ARC. So that's my talk. Thanks for your listening. Yeah. Miso, you haven't opened your speaker.
Hello.
Oh, Martin, okay.
Thank you very much, Professor Fan Wang. Very interesting talk, amazing work. Always great to see your work, and super excited for what you've done and what is coming next. As we go to the next step, I'd like now to introduce our next speaker, Professor Howard Lee. Howard Lee is our ICANX rising star, and he has done amazing work. He's also DARPA Young Faculty Awardee. He's also the DARPA Director Fellowship. He has been awarded the NSF Career. He's a Baylor Outstanding Faculty, and also is an OSA ambassador. So Howard, I'm not going to take more of your time. I'm going to let you jump into your talk. So welcome, Professor Lee.
Okay, thank you for the introductions. Let me share my screen first. Okay, I think you should be able to see my screen. So, so I'm Howard Lee from UC Irvine, from the physics department, at the same time from the Batman Institute. So at the same time, I'm also the optical ambassador. So trying to connecting the student chapter with the Optical Society as well. So first of all, we like to thank you, Alex, and also the organizer to invite me to be here to be able to tell you about my research. It's really a great platform to really talking about the research online. So what I'm going to tell you today is related to nano optics and meta optics. So basically studying optics in a really small scale. At the same time, studying some advanced nanophotonics structure on optical fiber so that we can have a advanced functionality. But before I go into detail of my talk, probably I just briefly introduce a little bit about myself. So originally I'm from Hong Kong, and I have an undergrad actually in the City University of Hong Kong. But in the last year of my undergrad, I actually have a chance to be an exchange student to Australia in Sydney. And at that time, actually I have a chance to work in the group in Kudos in Ben Anderton group. So working on research for the first time in photonics. So this year certainly is really game-changing for me, or life-changing for me, because it's the first time I kind of working on photonics, and also what I kind of having a passion on that. That's why I keep working on optics photonics for my career. But at the same time, also quite importantly, I also met my wife there. So definitely it's life-changing. So that's why I always encourage the student, undergrad, graduate student, if they have a chance to go overseas to see the world. At the same time, maybe we'll see the fire spout overseas as well. But anyway, after that, I moved to Germany for PhD in the Max Planck Institute for Science of Light in the group of Philip Russell. He's well known on photonic crystal fiber. And after that, I moved to Caltech as a postdoc in Harry Edward Water Group. So he's working on nanophotonic metamaterial and solar cells. So I think he's actually a speaker in 2 weeks in the ICANX talk. So after that, I moved to Baylor University in Texas as an assistant professor. And a year ago, I moved back to California in UC Irvine as an associate professor. So my group basically focusing on nano optics, studying nanoscale optics, and we have a couple of areas working on. For example, we try to look at the active plasmonic matter surface, making control on this kind of nano optic structure, and then integrating some of the matter surface nanophotonic fiber optics, and then studying some interesting material called seal index material. And then, for example, looking on some of the spectroscopy imaging, and finally making device. So we are in the physics department. We like to look at some fundamental physics, but at the same time, we also look for different application on imaging, sensing, communication, medical, even energy applications. So just to tell you a little bit about Irvine. So this is the map of Irvine, and UC Irvine is here, and we are in physics department at the same time have a lab in the Applied Innovations, and we also work with the Batman Institute. So Irvine is a nice city really close to the beach and for example, Newport Beach, and definitely want to advertise because we are actually looking for PhD and postdoc. So at the same time, welcome visiting scientists and collaboration as well. So if you know any good student, feel free to let me know. And if anyone like to come to Irvine, also happy to let me know and find some collaboration as well. So we are focusing on nano optics. So let me tell you a little bit about the nano optics. What's nano optics here? So you know that when the light enters the mediums, you have different fundamental optical property. For example, you have reflections, dispersion, and so on. So you have many fundamental optical property you have been already learned in high school for a long time. For example, reflection, transmission, scattering, dispersion, interference, and so on. And this we have been already understood really well for a long time. For example, the Sells law, we already discovered for more than 500 years ago. So it seems like everything is really well understood. We know really well in the textbook, etc. But this is exactly what we try to do in nano optics. We want to find something anomalous, for example, anomalous reflection, and so on, so that we have something completely different than what we learned in the textbook. And just try to refer to you, for example, one of my favorite scientists, Richard Feynman, he gave a really important talk around 60 years ago at Caltech. He mentioned that there's plenty of room at the bottom. So what that means is that when your material is going down to nanoscale, really small dimensions, all the property will be really different. For example, the material property, the electronic property, optical property will be really different than the bulk material. So this is exactly how what we want to do is want to study the light matter interaction in a really small scale. We're talking about in the nanometer scale. So we can do this because we have a really advanced nanofabrication nowadays. We can making the structure really small, smaller than a wavelength of light, or even smaller than 10 nanometer, 10, 20 nanometer. At the same time, we have a lot of new material we can use. For example, plasmonic material, 2D material, or some of the new material. I will tell you about that in this talk. So that's why we actually want to look at this kind of advancement here, looking at light matter interactions using new material, nanostructure, so that we can study some new physics, new optical property in the nanoscale at the same time, try to find some new application from this kind of nanostructure here. So certainly, nano optics is a really big field, so there are many different topics involved. But just try to give you one example. For example, one quite exciting topic is called a matter surface, and you can emergence. It's like an ultra thin optics. So this kind of matter surface, if you take a look on this structure, we're looking at the top view. So we basically have some scatter or resonator on top. So making nanostructure resonator, we basically can shaping the light in a different way. For example, the group from Capasso in Harvard, 10 years ago, for example, they're making this kind of structure. What you find normally the light will be reflecting in this kind of normal reflections direction, but now you can actually having an anomalous reflection and so on. So that means basically using this kind of nanostructure resonator, you can control or shaping the light in different way. For example, you can control the phase, amplitude, complex phase one, reflection, and so on. So basically, depending on how you design the structure, you can control the light property quite easily. So just to tell you how impressive on this kind of matter surface, you can see here, this is some of the titanium oxide matter surface, also from the Capasso group. We're also making similar structure as well, but you can see by patterning the structure, they can making a lenses, you can focus the light. And if you compare with this kind of matter surface lens with your optical microscope, you find they are really much thinner, much smaller. We are scaling down through order of magnitude, while we still preserving similar functionality as the lenses. So that's why this is quite impressive, because you can scale everything in a really small dimension here. But not only on lenses, could be also on different components, let's say mirror, beam splitter, polarizer, basically most of the component you can think of, you can have a meta surface version here. So that's why this is a quite exciting field in the last couple of years. And for example, there are a lot of fascinating applications or property have been discovered in this kind of meta surface. For example, creating a different polarization state, making a focusing lenses, ultra thin lenses, as I mentioned, controlling the polarization, manipulation and polarization, or even making device, for example, a holograph extraction. So this is really exciting because the physics is different at the same time. The application point of view is also different. At the same time, you can scale everything on your device really thin and really small as well. So this is really great so far. But if you try to take a look on most of the report in the last 10 years, 5 years, most of the report, they are focusing more on this kind of meta surface. They are passive. That means once you fabricate the structure, you cannot change the optical property anymore. So that's exactly what some of our motivation here is. Can we actually making a tunable meta surface using some conducting material? At the same time, can we use some extreme material to kind of enhancing this kind of tunability, for example, this kind of seal index material? And finally, can we actually integrating some of this kind of meta surface or even new material into a completely different platform so that we can have different applications, for example, in the optical fiber here. So this is some of the motivations. And if you just keep in mind, for example, if you have a conventional lenses, they're typically quite thick, couple of millimeters like my glasses. But now you can imagine you have a meta surface, it could be quite thin. But now if you can make it tunable, you can tuning the focus or even tuning different functionality. So this is some of the motivation in our research here is making active control to apply for different applications as well. So then this exactly go to the outline of my talk. I will first tell you about how we make a tunable meta surface, electrically tunable meta surface. I will tell you about this kind of really interesting material called seal index material, how we can actively control that. And finally, I will tell you how we actually completely integrate this kind of nano structure into a different platform, optical fiber platform here, so that we may have some advanced functionality here. So let me first tell you about a tunable meta surface here. So to make it tunable, there are actually quite a lot of different mechanisms you can think of. So we actually recently published a paper on active optical meta surface, kind of summarizing different mechanisms people have been using in the last 5-10 years. And this is 10 mechanisms, for example, electrical control using conducting material, 2D material, liquid crystal, or even quantum well, or using phase change material, mechanical control, using the substrate flexibility to change it, or even nonlinear optical property, chemical reaction, or microfluid tunability. So there are many different mechanisms that people have been trying to working on, but I will tell you that there are no one perfect mechanism so far in terms of really efficiently tuning this nano structure or meta surface at the same time having some fast functionality and different response, etc. But still, we think that actually this kind of electrical tunability using conducting material actually is one of the good candidate or mechanism to really making an efficient tunable meta surface. So that's why we have been working quite a bit on this kind of conducting oxide tunability. And this material we are using is a so-called transparent conducting oxide. So this is a heavily doped semiconductor. They have high transmittance in visible and near infrared range, which have been already been used for example, touchscreen or solar application, where you need the electrical tunability at the same time high transmittancy. And the good thing for this material here is that we can actually have a tunable optical property here. So to show you this, I'm showing you is a permittivity plot. So against the frequency or against the wavelength of light, assuming a Judah model, basically assuming a electron scattering, and we have a capital N here as a carrier concentration and plasma frequency here, and using a material called an indium oxide material. So then you can see that by changing the carrier concentration, you can basically shift the dispersion to a shorter wavelength. If you look particularly looking at, for example, optical frequency, let's say 1.5 micron, then what you find, you can have a optical, basically dielectric property. That means a permittivity positive or negative permittivity. That means a metallic property, depending on the carrier concentration of the material. So that means it's really good. changing the material property, you can change the optical property of this material here. And we can really change it quite significantly, and the way we can change it, there are different ways. For example, we can change it by fabrication condition, then you can change the doping, you change the carrier concentration of the material. But at the same time, you can also actively control it by electrical voltage, where you can have an active tunability. So that is one of the mechanisms we try to use, is using this kind of a field effect tunability by applying electrical voltage, which is similar to a MOS transistor. You have metal, insulator, and semiconductor here. But now if you're applying a voltage in between, because you have an insulator here, your electron will accumulate. They cannot pass through. As a result, your electron density will increase significantly. As a result, your optical property will change. So then to show you how this changed, this is an electronic simulation. You can see at the interface of ITO, by changing the voltage, you can see the carrier concentration can enhance maybe an order of magnitude. At the same time, you can change the permittivity from positive to negative. That means like a dielectric to metallic as well. So that means you can really see that you can have a really significant change on the optical property by applying voltage here. But one limitation here is that you can see the width here. We call this a Dipole length. It's actually quite thin, so it's only 1 or 2 nanometer here. That means your active region is quite thin here, 1 to 2 nanometer. That's why you need to combine with some of the highly confined structure, for example, this kind of matter surface structure, to make it a really efficient tunability. So that's why we actually kind of integrating to this kind of matter surface resonance structure using this active material. By applying the voltage, you can actively control the mode and also the phase and amplitude. So then if you take a look by applying voltage, you can see the mode actually change quite significantly. And that's why you can change the amplitude and phase of the light by applying electrical voltage. And what you can even do further is like you can gating the structure with different voltage. Let's say first one with different voltage, second 3 of them with different voltage, so that you can actively control the phase of the light. For example, you can have 0 pi phase shift here, so that you're making a phase grating here. So that means once you have a phase grating, when your light coming in, your light will be have a deflection to spear to different angle here. So you can do this by just gating the structure, let's say left and right and bottom with different voltage here. So then this is how we kind of tuning this metal surface. And this is some of the structure we have been fabricated already a couple of years ago. So like, for example, we have a bottom goal ITO here. But if you zoom in further, you see we have all the connection. We have the antenna inside. If you zoom in further, you see the antenna here. They are really small. We're talking about 300, 400 nanometer in size. But the good thing here is you can apply the voltage at the same time looking on optical property here, so that you can actively control the optical property here. So then this is just some of the result you can see by applying voltage. You can shift the resonance and also changing the amplitude for around 30% here. But quite importantly, is actually also controlling the phase, optical phase. You can see by applying voltage, you can changing the phase for 1 pi here. So, which is quite important demonstration, because we show that we can have a control of phase and amplitude, which is exactly what we need as a tunable matter surface here. So this is actually one of the quite first earlier successful electrical tunable matter surface using this field effect dynamic here. So as I say, we can actually gating the structure so that we can spin the light to different angles, so that we can even spin the light to around 140 degrees, depending on how you're gating the structure. And these mechanics are also quite efficient as well. They could be potentially quite high speed, could be 10 gigahertz or even more, and at the same time quite low power consumptions. And also we are only applying a couple of volts here. So this is a quite initial demonstration. This already report like a couple of years when I was a postdoc at Caltech. But recently, actually, people have been also quite a lot of advancement on this kind of field effect tunability. For example, in Water Group, they have been recently even able, for example, controlling the focusing or beam spinning at the same time using a similar structure, but you can applying the voltage and tuning the lenses focusing here. And at the same time, for example, the Samsung group recently also published work on using also similar structure, but now gating both on top and bottom, so that you have more control on this tunability. and they are able to demonstrate to use as a LiDAR applications, some of the initial applications on this kind of tunable metal surface here. So you can really see that there are a lot of advancement, really exciting mechanism we can tuning the light electrically. So we also recently kind of using this mechanism to make a tunable color filter. You can see by applying voltage, you can tuning this filter wavelength so that you can control the transmission as well. At the same time, you can also use it as a tunable absorber. By applying voltage, you can tuning the absorption of a thin film material here. So this is a mechanism for tuning this kind of nanostructure, metal surface structure. We really think that there are a lot of potential here. Particularly, we can looking at tunable lenses, tunable components, metal surface component. This could be quite important for example, some of the CMOS imaging system where you have bulky lenses you want to replace with a metal surface. At the same time, LiDAR application, as I mentioned. At the same time, some of the virtual reality, AR, VR, where we need really a lot of optical components, holograph lenses, etc., where you can use this kind of metal surface or tunable metal surface to advancing some of the functionality. At the same time, we reducing the sizes as well. So, we will paper recently, actually, we kind of summarizing what kind of potential applications you can kind of think of using this kind of tunable metal surface, ranging from communication or even fiber device, LiDAR, or even for light cell, or AR, VR, or even ultra-fast technology, or even image encoding. So we really think that there are a lot of opportunity here, but at the same time, we still need a lot of different research, enhancing the efficiency, the speed, and so on this mechanism here. So this is the first part about some initial work on the tunable metal surface. Let me move on to the second part to tell you something on really exciting material called a seal index material here. So what does this seal index material or epsilon near seal material means? The epsilon here means the permittivity. That means this material have a permittivity close to seal. So typically, if you know the metal have a negative permittivity, that's why you see it shining from the reflection from the metal, and dielectric have a positive permittivity. And epsilon near seal material means you have a permittivity close to seal in certain frequency or certain wavelength of light. And in this really extreme regime, so you will find really a lot of extreme optical property. You can find, for example, you can confine the light really strongly. At the same time, your reflective index could be quite small. That means your velocity could be really high as well. So that means you have a lot of extreme property you can find from this kind of ENC material. And the material we have been using on this kind of a seal index material is actually this kind of conducting oxide material, as I showed you before. And if you try to take a look on dispersion of this kind of material, you find they actually have a seal causing one near infrared or visible range. This is exactly the ENC regime we are talking about here. So in this regime, there are a lot of extreme optic and physics we can find when you shine light on this. And one of the things is that you can actually excite this kind of ENC mode or even making it a perfect absorption property. So basically, it's quite simple. You just have a thin layer of this ENC material. In this case, we have an ITO material. By shining the light with certain angle, you'll be able to excite this ENC mode here, so-called ENC mode. And once you excite, what you find, basically all the optical field, all the light will be confined on this ENC material here. So what's that mean is that you can also have a really strong absorption. If you look at the absorption, so then you can have some condition to have a perfect absorption, and depending on the K concentration, you can shift this perfect absorption to different wavelength of the light here. And there's just to emphasize here, we're talking about this kind of ENC material could be really thin. We're talking about wavelength divided by 50 or divided by 100. That means we are talking about in the visible range, we're talking about the thickness will be maybe less than 10 nanometer or even smaller than that. But at the same time, you may need a certain combination of angle and thickness in order to excite this more efficiently. So that's why to study this seal index property, we need to have a good control on the material in terms of the ENC wavelength and in terms of the thickness here. So that's why we actually have been using this a technique called atomic layer deposition technique to making this material. So this layer by layer deposition technique. So that means you can really control the thickness quite precisely. At the same time, in each layer, you can control the conditions so that you can have different material by this ALD deposition. So just to give you an example, we deposit the aluminum zinc oxide ACO. Depending on the zinc oxide and aluminum ratio, you can really tune this ENC wavelength to different region in the telecommunication wavelength. And just to emphasize again, this ALD allows you to precisely control the ENC wavelength and thickness, which is something quite important for this ENC optics study here. So at the same time, this can also provide quite good quality of the surface. At the same time, you can also coating it conformally. That means if you have a metal surface, you can even coating the side wall of this metal surface quite easily. So that's why we have been using this technique quite a lot to making this kind of ENC material here. So then to look at the measurement result, we basically just put it in a sample here, and then we have a supercontinuum light source. That means a broadband light source, and coupled to different polarization state, and then you can excite with different angle and collect with different angle with a spectrometer here. So then just to show you one of the 15 nanometer thick ITO, this is the measurement result. You see in the reflectant, you have a strong reflecting dip, which is correspond to the ENC mode excitation. And if you take a look on this absorption band here, it's around 20 dB here, which is correspond to around 99% absorption here. So you can see it's quite impressive here. Only 15 nanometer of a layer, you can absorb almost 100% of light here. At the same time, I mentioned to you, this excitation is really depending on the thickness as well. So we try to use the ALD to making different thickness of the material. You can see by reducing the thickness, your coupling will significantly reduce at the same time your ENC wavelength shift here. So that means you really need to have a precise control on the thickness in order to excite this mode efficiently. And that's exactly the ALD can do, because we can fabricate quite precisely on the thickness here. So then we're able to demonstrate, for example, making this as a perfect absorber, as I mentioned to you. Using one layer, you can absorb almost 100% of light. But at the same time, you can also make a broadband perfect absorber by stacking multi-layer. Now, different layer have different carrier concentration, that means different ENC wavelength. So that's why you can have a collective response, so that you can have a broadband absorption in this case. And at the same time, we can also use the tunable mechanism I mentioned to you. Applying the voltage, we can tune this absorption band here to different wavelength of modulation for more than 100% in the absorption here. So at the same time, just to side chat a little bit, recently we also tried to using different mechanism to design this kind of ENC material as well. For example, this kind of multi-layer structure. Once you have a really complicated or many layer, you have a really complicated combination here. That's why we have been using neural network to try to optimize to make a broadband absorber. For example, this some of the result. You can see that in an 8-layer structure, we can using a neural network to make a broadband absorber for around 520 nanometer, which is really a large band with perfect absorption here. And total thickness is only 40 nanometer, 48 nanometer. It means you can have a really ultra thin ENC material at the same time have a broadband response here using this kind of neural network design. So far I told you mainly they're all linear optical property, but this kind of seal index material, ENC material, they actually have quite interesting nonlinear optical property as well. So nonlinear means when you have a really high laser pulse, you will have a nonlinear response on the light. So for example, people are able to look at some of the so-called curl nonlinearity to change the refractive index by using a nonlinear optical pulse. And also to create a high harmonic generation, creating multiple color by using this kind of high nonlinearity of the material, or using the refractive index close to seal, have a phase matching free nonlinear propagation, or even used for nonlinear optical switching, so that you can have an ultra fast switching using the high nonlinearity. So this is quite exciting field, and at the same time, really using this advantage of this ENC material here. That's why we have been looking on this nonlinear effect quite a lot. At the same time, we want to see if we can using this layer engineering on this kind of ENC material to enhance this nonlinearity, so that we can enhancing the nonlinearity in a really thin dimension, really thin material. So then we have been using this kind of ALD fabricated material at the same time, using so-called a C-scan nonlinear measurement to measure the nonlinearity, which is a really simple measurement. I try to simplify the setup certainly, but basically you have a femtosecond laser here, we have a sample, and we have detector here. But what we do basically, we scan on the C direction, so that when you scan on the C direction, your intensity is different. As a result, your refractive index change due to the nonlinear high power laser pulse will be different. As a result, your spot size you can think of this will be different as a result. When you detect in the detector, when you scan in the C direction, your detector will have a different response. So then using this kind of C-scan technique, we actually able to retrieve so-called a nonlinear reflection and with absorption. So I try to simplify here, but just to put you the result here. And for this sample of ACO with 76 nanometer, and this nonlinearity actually already 5 order magnitude higher than a few silica glasses. What I mean is that if you have a silica glasses, if you have 1 centimeter, in order to control the phase using a laser pulse, you only need around 100 nanometer of this ENC material to obtain a similar optical phase change using the same power pulse. So that means you can really reducing the size of the material you use because of the enhanced nonlinearity of this ENC material. So this could be have been quite exciting, but at the same time, we also want to try to look at a little bit more on, for example, how we excite with different angles or different wavelength, because we know this ENC mode excitation really depending on the angle of excitation and also the wavelength. So in certain wavelength and angle, you can have excite this mode more efficiently. So then we have been also looking on the thickness dependency as well, because we know that this kind of optical confinement is inverse proportional to the thickness square. So we want to see if we can reduce the thickness in order to enhancing the nonlinearity here. So that's why we have been fabricating different ENC material with different thickness here, 76 and 200 nanometer, and looking on nonlinear coefficient. You can clearly see that so changing the angle, you have a certain angle, you have an enhances nonlinearity. At the same time, the thinner sample, you also have a certain enhancement here because of the enhanced optical field here. So we can clearly see that we have some angle and thickness dependency because of the ENC mode excitation here. And this kind of enhancement could be even further enhanced if we reduce the losses of this material. That's why using some of the nano engineering of this material could further enhance this nonlinearity as well. And we also try to look at the time response of this. So we try to use a standard pump probe technique and try to measure the time response. This typical delayed response you can see. So we have a relaxation time of around 130 femtosecond, which means like quite high, quite fast nonlinear effect in this type of ENC material, which is quite important because you want to enhance the nonlinearity at the same time also have a quite fast response as well. So I try to skip some of the details here because I don't have time to tell you all the details, but I want to kind of summarizing that to tell you that we're actually able to control the nonlinearity by looking have different thickness at the same time to enhancing the field confinement of the material can enhance the nonlinearity. And we also find some really interesting nonlinear physics and electron dynamic on this steel index material at the same time, the enhancement as well. So we really think that this could be really important for different applications. Certainly, we want to integrating this nonlinear material to nano structure. So, for example, we can think of this kind of metal surface structure. We can coating an ENC material. At the same time, you can apply the voltage to control the optical property. At the same time, enhancing the nonlinearity as well. So at the end, maybe you can kind of electrically and optically tuning this kind of light generation so that you can use it for ultra-fast holograph image encoding nonlinear metal surface or even ultra-fast optical sheet. At the same time, also quite important, you can think of like integrating the nanophotonic structure. For example, this kind of plasmonic structure, you can coating this ENC material by shining an ultra-fast light. You may be able to modulating the signal. So for example, you can have a directional coupler with a bar and cost. By putting a high intensity output with a ENC material, you may be able to switching between the bar and cost. At the same time, if you have compact wave resonator, you can use a non-linearity to switching or even routing the light to different ports as well. So we really think that this ENC material have some enhancement on non-linearity, which could be really taking use of this kind of nano device here. So let me move on to the last part of my talk. I will try to tell you how we can integrate some of this metal surface or steel index material I have told you so far to a completely different platform, to the optical fiber platform here. So for those of you I may not know too well about optical fiber is made with glasses. We have a core, we can guiding light because of a high reflective index, we can have a total internal reflection and guiding light in the core. And this has been really important for telecommunication because we have been using this optical fiber to guide light for really long distance. At the same time, we have a really fast communication system nowadays. So this is really important technology in my opinions, because if we don't have this kind of high-speed internet, I can't even chat with you in Zoom now, telling you about my research. And at the same time, we cannot even, for example, looking on some other movie or even talking with people in WeChat and so on online. So that's why this is a really impacting technology. That's also why the father of the fiber optic, Charlie Kao, got a Nobel Prize more than 10 years ago. And on his contribution on using this simple physics phenomenon, total internal reflection, to apply to optical fiber communication technology, making a huge impact on the communication system at the same time on our human life as well. So definitely it's a great mechanism to guide light. At the same time, we have a really good technology nowadays. But I want to tell you that we still actually have some limitation on this kind of optical fiber we have been using. We have some fundamental limitations we cannot overcome. But just want to also emphasize that other than communications, we also have other applications, for example, imaging sensing and fiber laser, which really rely on optical fiber. But as I mentioned, it's like we actually have some fundamental limitations on this kind of optical fiber we are using, because we are limited on the glass material we are using. At the same time, the geometry we need to guiding light in a single mode, for example. So then we have a restriction on also the material restriction, where we cannot guide light with, for example, high power, high speed, and so on. At the same time, once you fabricate this kind of optical fiber from a fiber joint tower, all the property is fixed. For example, the phase, empty, or polarization is fixed. You cannot control it anymore. But you may say that actually you can also find some optical fiber component, for example, from ForLab. For example, you can find collimator, lenses, modulator, insulator, and so on. But you can see that all of these are really bulky. They are not really a tiny component here. At the same time, they may not be too efficient and also quite costly as well. So this is exactly why my group is kind of want to integrating some of the things we have been learning from the nanophotonic field, for example, this kind of metal surface, or even new material, steel index material, or even plasmonic material into optical fiber to make a new kind of optical fiber. We call this metal optical fiber with an advanced functionality here, so that we can, for example, having some new functionality, minimizing the size of the fiber component at the same time, having a new optical excitation platform for different applications here. So that's why this has been something we have been working on and kind of passion on in our lab here. But at the same time, kind of longer term, we actually also want to make it tunable as well, so that we can actively control all the property coming out from this optical fiber here. So that's why in our lab, we have been working on, for example, integrating metal surface, nano wire, or even nano circuit in the optical fiber, to advancing the functionality. And just keep in mind, some of this metal structure we're talking about, they are really small. So the optical fiber is like a human hair. And now we're actually making tiny structure at the end phase of the hair. So they are really nanoscale. So we're really integrating nanoscale structure to a micron scale optical fiber here. So then I will just show you a couple of demonstrations on different devices we make. For example, first thing we make is a kind of a lenses, metal lenses on fiber, so that we can focus the light directly on the end face of the fiber using an ultra thin component. So To design a lens, we can take what we learned to making my glasses. For example, typically you need a certain phase curvature to focus the light in the conventional lenses. And if you try to take out the textbook, you find you need a certain phase profile in order to focusing the light as a lenses. For example, this lens, you need this kind of phase profile. For another lenses, you need another phase profile. But what we do basically on this kind of metal surface, you have an ultra thin component, and what we use is using so-called geometric phase here. By rotating the structure, we can control the phase, and at the same time, you can preserve the efficiency. So that means you can control the phase by just rotating this tiny nanostructure here. So that means we produce this phase distribution by just rotating the structure of this metal surface unit cell. So then you can obtain the similar phase you need. And if you want to design different lenses, you have different phase response, then you just need to have different rotational distribution here for the other lenses. So then the way we make the lenses is using a photonic crystal fiber. I try to skip the reason here, but basically we can have a more bigger size of the core. But what we do then, we basically coating the metal on the surface, and then we try to use a focus ion beam to mirroring the nanostructure on the end face of the fiber. So then my student able to make a really beautiful structure. So you can see that inside the core, you're gradually rotating the structure from the core to the outer core here. And so they can create this phase profile to focus the light as a lenses. And this is for certain lenses, certain NA of lenses. You can decide the structure of the different NA to focus the light by just changing the rotational distribution. So just keep in mind again, as I say, this is an optical fiber. It's like my hair. We're actually making tiny structure on the end face of the core, which we can't really see by eyes. So, but you're actually able to measure this kind of lensing property. We are using simple setup. We have tunable laser here. We have a metal surface at the ends of the fiber, and we have an imaging system here. So basically what we do is scan on the linear C-scan. So then once you scan, you find a certain position, you have a high intensity, and this is exactly the focal length we are looking at. So the light is focusing as a lens at this position. So then we try to do different measurements. For example, for the fiber with this NA of lenses, you see different wavelength. We have a focusing effect with a similar focal length. And by changing the lenses, you see we also have a different similar focal lengths with the different wavelength, but we can change the focal length quite easily here to 40 micron. Compared with simulation, we have a similar result in terms of the focal length and also the beam width here. So just to give you a little bit number here, this is the focal length. You can see across this telecommunication wavelength, we have a really constant focal length here on this fabricated structure. And the efficiency here is around 15% in the telecommunication wavelength, which is also quite decent as well. So, but certainly this could be further improved because we're using metallic structure. They are actually quite lossy. And we actually find that if we try to use the dielectric, let's say a silicon metal surface, we can enhance the efficiency to 91%. So which means really high efficient lenses on fiber. So this is so far making a lenses, and actually we can also making a filter on a fiber. So then we basically making tiny nanostructure, but we actually can making an asymmetric structure so that you can have some polarization dependency. So because of time, I will just quickly go through this. So we can making a uniform symmetric structure or asymmetric structure, and at the same time on photonic crystal fiber or standard optical fiber. And if you try to see symmetric structure, you see for two polarization state, you have a filter with the same wavelength range here. But now if you have an asymmetric structure, you can making a polarization depending filter. Depending on the polarization, you can have different color filter coming out from this optical fiber here. So this is matching also quite well with the simulation. I told you about this tunable or kind of a metal surface structure, but as I say, the longer term goal is actually really making it tunable so that we can making use on different application, let's say endoscope application, where you need to imaging inside the body. There are a lot of components you need to use. So for example, scanning elements, this kind of metal surface or tunable metal surface could be really useful, or even for laser surgery, using a fiber. But now you don't have a really good control. You can using this kind of metal surface or tunable metal surface to confine the light or even controlling the polarization and so on. So we really think that there are a lot of different potential applications in terms of this kind of fiber for imaging, endoscope, laser surgery, or even for communication system for multipassing, or even develop some fiber device, or even pulse shipping on optical fiber. So just one last slide is like other than metal surface, we also kind of integrating ENC material on optical fiber in different platform here. We really think that integrating this kind of zero index material on fiber could open up some different opportunity. For example, we can have a different excitation platform, longer light matter interactions. At the same time, you have an automatic phase matching where we can develop different kind of zero index optical fiber and functionality. But because of time, I will not be able to tell you any result here, but we really think that this could be something also quite exciting as well. So let me acknowledge the people in my group. So as I say, I moved from Texas to Irvine recently, and all the group members, without their hard work, I cannot tell you all the results here. And also acknowledge the collaborator and also my peers advisor, for example, Philip Russell and Harry Atwater, and the people in the US, Texas A&M Naval Research Lab, and Europe, and also for example Asia, from China, Hong Kong, Taiwan, and Diping Chai, Yuan, and also the funding agency supporting our research in the last couple of years as well. I think that's the end of my presentation, and we'll be really happy to answer any questions. Thank you very much.
Thank you very much, Professor Lee. Really exciting work as always. It's always nice to see what you're doing. We're going to switch now to the Q&A, and we have two questions from the audience. The first one is for Professor Wang from Xi'an. Thank you. Let me share this. Thank you for your wonderful talk. As you mentioned in the second part, you doped the nanoparticle into cells. Can you control the location precisely, and how do you reduce the damage?
Okay, so pretty good question. So it's not like we dope it into the cell. It's more like just like a dye. Just like a normal dye or a quantum dot dye, you can select a different, like for example the nuclear or the certain like mitochondria or something. Just you need a coded nanoparticle with certain antibody and then link it with another things, and then you can control like which part of the cell you want to target it. Yeah, but yes, you can control the location and how to reduce the damage. So for this, it's not really clear what kind of damage, but just by like dye this particle onto the cell, don't have any damage. But if you really like use really high power shining on nanoparticle and on the cell, it may damage the cell a little bit. But generally, we did some tests. If you're using 100 milliwatt, which is really high, and near infrared light shining on cell, still can survive 2 hours. So it's long enough for us to tracing some like event. Yeah.
Very good. The next question is for Professor Lee. In the layered materials, what is the role of interface dipole in your measurements, and how do you address any distortions from these devices?
Yes, it's a good question. So at the moment, we actually haven't taken into account on that. So we're kind of assuming it's a uniform layer, and also the K density is uniform. But we actually also trying to do is like certainly there may be some charge accumulate in the interface between the layer. We can do an electronic simulation to taking account on some of these carrier accumulations. And at the same time, if we're kind of knowing the worthless, we can also introduce in this kind of modeling as well. So, but at the same time, if we have really multi-layer, let's say 10-layer structure, as I say, I think using the neural network is something could be really significant to enhance this kind of modeling, because we find actually there are so many combinations Just using a normal forward simulation, it's really hard to predict the optical property.
Very good. So now we switch to the panel. Professor Kim, you're muted.
Sorry again. So we can start our panel discussion. So it can include our questions for the speakers, and we can talk about our life at perspective, like as a academic career. So, yep. Martin, do you have any questions first, or?
I actually got many questions for Howard.
Oh, okay. That sounds great. So you can start, Wang.
Yeah, I really. So Howard, thanks for your wonderful talk. It's really interesting. Yeah, and some of the field really connect to my research. So this is why I want to ask a few questions. So first of all, you mentioned that you can tune in the refraction index for 10 gigahertz, right? In the first part. So super fast. Are you? Did you think? Have you tried to use this? Make some device like a spatial light modulator, because the current is on the liquid crystal, so speed only 60 hertz. It's like a way slower than you want. Yeah.
Yeah, that's right. That's right. So that's why. So the 10 gigahertz is a kind of a prediction, but we actually able to demonstrate like I think 150 megahertz or even higher. But this really depending on how you adjust with the algorithm. That means this mechanics are really ultra fast. That means you can really go up to 10 gigahertz or even faster. So that's exactly the advantage, as you say, compared with some other mechanics, like liquid crystal, etc. People have been also integrating the metal surface, but that could be quite slow as well. So that's why this conducting oxide field effect could actually having some really good advantage on that. And you're actually right. So people have been trying to making a kind of nanoscale spatial light modulator based on this kind of tunable metal surface. I would say at the moment it's still kind of in the research stage, because when we're talking about efficiency, etc., we're talking about all the time maybe 5%, 10%, etc. And that is not compatible at the moment with the commercial spatial light modulator. At the same time, some of these mechanisms, for example, the one I showed you is based on some of the reflective metal surface. So this also posing some of the, let's say, application difficulty. For example, sometimes you may want to have a transmission phase control. So then that's something actually the community have been working on. And that's also sort of the things that I mentioned in the MRS meeting in Hawaii. People have been bringing up this kind of questions and trying to bring some different good idea. But I would say this is still a relatively new field and also exciting field. People have been really addressing some of this challenge here.
Yeah. Okay. Nice. Thanks for your answer. And because we currently doing something like different but slightly close, we are doing the tungsten oxide one. So we can also change the refraction index, but this by loading the ions, its response is extremely slow. But we can change the reflection color. So, but I see your tuning with the ITO is really. Yeah, it's really fast, fascinating. And another question I want to ask is, have you tried to, because for your one, you can tune in really fast and you can generate you should be able to generate some scattering pattern really fast. Have you think about, because I'm doing imaging, so I'm also doing the ghost imaging. Have you think like combine these two fields, like using some general like scattering pattern to doing something?
Yeah, so that could be something quite exciting as well. So people also kind of also start to working on kind of a time modulating of let's say the transmission, scattering, etc. So that is some possibility here as well. So that's something we actually want to look at as well, particularly, for example, for imaging, as you say, or even if we can integrating the optical fiber or even able to make it tunable, that could be quite exciting. But again, at the moment, it's still some limitations could be the efficiency or let's say how big the structure we can make, etc. So that is something practically we need to think more as well. But I would say this is really opened up a lot of different potential for imaging and even this kind of super resolution imaging as well. So we'll be quite excited to talk with you more and try to see any collaboration as well. Yeah.
Maybe we can build some collaboration. So one final question. So for the fiber one, if you make the layer like really thin, like let's say 50 nanometer or something, like is that gonna be, what's the loss of the light? Like what's the efficiency of the?
So yeah, because if we are using for some metallic structure, so we still always talking about maybe 20-30% will be the maximum we are looking at. That's right. But as I say, if we using a dielectric structure, so that there will be really low loss metal surface, then that could be really high efficiency, 90% or even higher. But then the dielectric structure is actually more difficult to fabricate than metallic structure. So because we need to use an E-beam lithography to pattern on the optical fiber, which is really different than a group have been successful. For example, the big group in some of the and also in Germany and also Microscopy group, they actually also kind of using a 3D printing as well. So now printing a polymer material, which is quite easy to do. Then you can printing on the surface and making a lenses. Yeah, that could be quite something quite interesting area to.
Yeah, I saw that work. Yeah, they can print in. Oh, well.
I think I kind of disconnect this. I come back here, but I just say I want to say my final conclusion is like certainly the polymer is great, but you may not be able to use high power in terms of that. So, but there's a lot of different exciting direction to work on.
Yeah, I also saw they using a 2D material on the end and like a geo or something other thing. It's also really high efficient.
Yeah. So yeah.
Okay, when Howard disappeared, I thought that he's using the optical metamaterial for optical clocking.
Yeah. Also fast cooking. Yeah.
Right. So I have to say this, since I'm working in acoustics and mechanical metamaterials, I have to thank all those people who are working on metamaterials in optics, because when they design very nice things, we actually follow something. So we just adopt the design again and again, like a few years later. So we are kind of the followers, and thank you for your great work in optics.
Thank you very much. But we also always follow the acoustic people as well. So we need to scale down the structure as well sometimes.
Yeah. So we scale up. So from your design. Okay. So can I have a question for Fan as well?
Oh yeah.
Yeah. So I'm very ignorant in this biophotonics, but I was wondering, since you the cells that your specimen has some limited lifetime, so when you do the experiment, that would impose any challenges in your experimental process?
Yeah, actually the lifetime is really long. So usually when using the for example dye or just a quantum dot, the lifetime is in nanosecond, 1 nanosecond, or hundreds of picosecond. So for that one, if you're doing the scanning, single beam scanning, you can scan really fast because all the photons squeeze out in the really short time range. But for us, the lifetime a little bit like long. So it's about like hundreds of microseconds. So actually really long. So if we scan for really short time, really fast, you will see like each of the pattern will have a long tail. So this gives a little bit trouble. But we can just by tuning the lifetime, like heavily doping, we can reduce this one. So currently what we're using is fun. But at the end of my talk, I mentioned that recently there's a rising field, is basic emergent field, is on the photo avalanche effect. Means like really high nonlinearity. up to like 40 or something for nonlinear slope. For those one, you need like even close to a second time to build up your photo avalanche effect. So for that one, if you want to do the imaging, have some challenge. So currently, we're also doing some research try to solve this one. And after solve this one, if you use this probe onto the imaging, it's gonna be fantastic. So in future, it's pretty much like for all of the confocal, you just need to change the dye, you can do superrise. You do not even buy some equipment or something. Yeah.
Sounds great. Thank you. So Martin, do we have more minutes or do you have any questions?
No, I have a question for Fan. Actually, related to what Professor Kim is asking, you know, when you're working with biosystem and light, you have a lot of potential absorbing molecules. How do you compensate for any possible stochastic biointerference in the signal you're getting? And could that be mapped out from the distributions of your peak? Because I saw some of them have tails. And is that a tail due to the optical response, or is it because the environment you have has potential interfering molecules? And how do you map that out?
Yeah, so for us, what we're doing is the fluorescence imaging. So basically the interference is not, assume that you mean the interference is like when you're doing some like interference type image, right? Like the reflection of the tissue, no?
I'm thinking, for example, if you have in fluorescence imaging, if you have a tryptophan very close to your sensitizer, it can quench the signal, right?
Okay.
So if I have a lot of molecules like that near your particle, are they close enough that they can cause absorption interference, or will they have secondary emission behavior? And if you have something like that, how do you take care of that?
Yeah, so really good question. So actually, this is the benefit of this upcountry nanoparticle. So this is not like a fluorescent dye or something, they have some quenching or something, even some like, if you put some gold particle, you do have this quenching, but when they aggregate, they didn't change the emission property, because for each of the particles, they already have like this density of the emitters inside. So they already have the crosstalk, the interaction between each of the emission dipoles. So whatever is the so each of particle have 2,000 of emitter and 4,000 of sensitizer. So they already have like bonding together. So this is a good thing. So this is why it doesn't affected by the surrounding material. Yeah.
Okay. Okay. And do you have any issues with biofouling, like aggregation, because you have the binding, the binders that you use to direct the particles?
To be honest, we do have this problem. Okay. So when we try to label the cell, they tend, because they are really big, basically. So if we reduce the size to 12 nanometer, it's much better. But when we reduce the size, we have some defects, and also the emission efficiency is not that high. So usually we use 24 or something, but 24 is pretty big. So when we like address this on the cell, we do have aggregation problem. It's not like working really well as a normal dye. Yeah, because normal dye size is like close to 1 nanometer. So yeah, we try to solve this one, but pretty hard.
Yeah. Very good. And the next question is, I'm going to ask it to Howard, but it's technically both for you. For somebody who is looking at the field in your talk, and you present very amazing talks, you know, the data is amazing. And there's somebody out there who would like to hop onto the field. But when they look at Howard's images, the patterns look so beautiful. The fabrication methods are so hard. And if somebody has no experience to that, they might be intimidated. The entry barrier into the field might be very, very high. Is there space for things like self-assembly and other more affordable techniques? Let's say somebody doesn't have access to an ALD, they don't have an RIE, or they have no etching systems. Mm-hmm. How would they be able to get into the science without having super high-tech systems. And the same thing for you, Fan. You know, those synthesizing those particles is not trivial. So how does somebody get into the field without having $1 million or $2 million to get set up?
Yeah, so it's a good question. So yeah, I think definitely we have different part in our research. So for example, we still need to understand more like the property before we even fabricate. For example, we do a lot of numerical simulations, understandings, and trying to let's say modeling some of the nanostructure or even this kind of like ENC material, etc. So that will be some part that could be more easy to start with, or you don't need a really high kind of high ANC equipment. But in case if let's say your university or your lab is not capable to fabricating some of this material, is the easiest way is I think is collaborating with people. So because sometimes we also not able to making all the material, all the good structure, etc. So sometimes we also collaborate with different group. They are expert on that. So I think that is something we can kind of sharing different resources, but at the same time trying to move forward on the research. And at the same time, like at some point, there's some material we have it commercial available for some of this kind of ITO as well. That could be some things you don't need the equipment. You can just buy maybe a couple of samples to look at the optical property. For example, some of the paper on nonlinear paper I mentioned is like people publish in Science. They actually even also getting the sample from companies. So that could be maybe $10, $20 for a sample. So that is something possible. I think more important is just to don't limit yourself, think a little bit bigger and try to see what is interesting and try to find something new to work on. And again, depending on the resources, you may have a limitation, but probably find different opportunity, collaboration, or a different company to work with. So I think that may be my advice.
Okay, very good.
A wonderful answer. So how many more minutes do we have here?
We have about 6 more minutes.
6 more minutes, then I'm allowed to ask questions, right? So I have a question for both of you. So the thing is, we are all like in the beginning and then in between of like a beginning to mid-career now, I guess, me either. So I was wondering how you can advise your students, how you can guide your students. So can you share your wisdom of advising your students and how you teach your students in your lab? Not undergrad, so the graduate students. So Ben first.
Go ahead.
Okay, me first. Yeah. So so for the student, yeah. So for me, it's like just because for students, they're all different, have totally different personality. So I guess for me, it's just according to their different like personality, I gave them different tasks. For example, for some students, really smart, and so he have lots of idea. I gonna encourage him to like lead lots of product by himself. And in the future, it's really easy shaped him into like a subgroup leader or something. So because he got many ideas, he just need more hands. Yeah. And for some students, they don't have that much idea, but they're working really hard. They have passion to working on the project. So I usually like put some really big project on them, like maybe 3 year, maybe 4 year. And so he can stay on this one project and doing like, so yeah, so but the different personality basically give different tasks. And in future, all of them can, I'm not really sure all of them want to be staying academic, because staying academic is really, to be honest, it's really hard, and we have to working really hard. It consumes lots of our energy and lifetime actually. Yeah. So I'm not really sure all of them want to do like a professor or like staying academic, but I try to like lead them to the way like they can do, they can full use their like intelligent, full use their knowledge. Yeah. And why teaching them, I basically first ask them what they want in the future or what's the field they like, and according to what they want to do. And then, because during the 3-time or 4-time PhD is still really limited, so they can only learn certain type of technology. So they couldn't waste their time. So have to have some plan at the 4th year, like what did they learn? And so they all benefit myself actually. So for example, now I have like, I have almost 6 students already graduated and they have different technology. So every time when I need something from them, I just I directly call them or something, and then I can get some help. Yeah. Yeah, I'm not really sure I answered all your question or not.
No,
but
no.
Yeah.
It's a really a wisdom that I wanted to hear. So thank you. I'm learning. So I'm learning from you. So thank you. So Howard, I'm sorry that I asked a difficult question. This is quite challenging, I know. Because this is something I always ask myself.
So I can think about it when Fan is answering. So
Yeah,
it's good for me. So yeah, I think really important, as Fan also say, like I think the passion is really important. You need to keep the passion to keep doing good research. If you have passion, then you have energy, you have really spending time on that, which is really important. And I think you really need to find opportunity yourself. There's so many opportunities coming up from yourself. So you really need to, let's say, try your best to go to conference or talk to people thinking more new ideas. So, because again, opportunity you create by yourself. And yeah, finally, probably hardworking is really important. So yeah, without hardworking, I think it's hard to making things work. But if you have passion, then certainly you'll be working really, have all the energy to work on one thing. So I think that's just my advice. And I can give an example. So for example, probably Alex know about that. So I was actually in one of the finalists on the light competitions. I didn't get it at the end, so unfortunately, but it's quite upset. But still, I kind of not giving up and keep trying and trying just to do the things I like, sharing the research. And at the end, I got the Young Scientist Award for mechanics. So there's some things like similar to what we are doing in the lab. It's always fails, but just keep your passion, working hard, and at the end, it will be successful. I think that's what I want to share.
Thank you so much. Thank you so much. And I'm very sorry for asking difficult questions.
That's what we're here.
Yes. Yeah, I just want to say Howard and me pretty much all have some similar experience, like when we submit some paper and always like rejected and transferring, like, so if you're doing academic, so this like gonna be usually happen. Like if you submit to Nature and rejected to Science, reject. So, or you have a long list of journalists and have to do this like every month, something like that. Yeah. So you have to be used to like touch this kind of like fail. Yeah.
Very good. Thank you very much, Fan and Howard. It's always great to have you on ICANX. And please accept this virtual plaque for your presentation, Howard. We're going to share with you this virtually, and so the same with you, Fan. We're going to be sending this to you. So we're so grateful for your continued enlightenment in many ways, literary and philosophically, with your work on light. Yep. And then for everyone else, we want to remind you that next week we have a super talk from Manish Chawala from University of Cambridge. And the panelist is a superstar panelist, Chris Nyhouse from Trinity, Shelley Cradich from Purdue, Leo Tao from Southeast University, and Mayo Shi from Imperial College London. And the discussion is going to be on 2D materials and energy conversion and storage. We welcome you to join. It's going to be fantastic. And with that, thank you everyone. Great talk, and see you next week.